Have you ever wondered what sound really is, or how we can hear different types of sounds? Let's delve into this fascinating world to find answers. At its most basic, sound is a type of energy made by vibrations. When an object vibrates, it causes the particles around it to move, creating a rippling effect much like when you throw a stone into a pond. This ripple, or wave, moves outwards, and voila, we have sound waves propagating through the air. But air is not the only medium sound can travel through. These sound waves can also journey through water and solids. Picture the strumming of a guitar string. The vibrations from the string are transferred to the air, then to your eardrum, and finally to your brain, which interprets these vibrations as sound. But if you press your ear to the guitar, the sound is louder and clearer. That's because solids, with their closely packed particles, can transmit sound waves more effectively than air. Now let's introduce the particle model of matter. This model posits that all matter is composed of tiny particles that are constantly in motion. When these particles vibrate, they pass on the vibrations to the particles next to them, and so on, leading to the propagation of sound. So whether it's the chirping of birds, the rustling of leaves, or your favorite song, all sounds are brought to you courtesy of these tiny particles in motion. But remember, sound doesn't always need a physical medium to travel. It can also travel through electromagnetic waves in the form of radio or television signals, reaching us even in the vacuum of space where no particles exist to carry the vibrations. So, sound is not just what we hear, but a fascinating interplay of energy, matter, and vibrations. As we journey further into the world of sound, we'll discover more about its intriguing properties and the myriad ways it influences our lives. Now that we understand sound, let's delve into the world of frequencies that are beyond human hearing. Ultrasounds and infrasounds. Ultrasound waves are sound waves that have a frequency higher than the upper limit of human hearing, typically above 20 kilohertz. These high-frequency waves can be used in a variety of applications. One of the most commonly known uses of ultrasound waves is in medical imaging, specifically in ultrasound scans of a fetus. This technology allows doctors to visualize the fetus inside the womb, providing crucial information about its development and health. On the other hand, infrasound waves are sound waves with frequencies below the lower limit of human hearing, typically less than 20 Hz. While we can't hear these low-frequency waves, they can still be detected and measured. Infrasound waves can be produced by natural phenomena such as earthquakes and thunderstorms, but they also have practical applications. For instance, infrasound technology is used in the detection of atmospheric nuclear explosions and in the study of animal communication. Let's dive a little deeper into the animal kingdom. Both bats and dolphins use ultrasound waves in a process called echolocation to navigate and find food. Bats emit high-frequency sounds that bounce off objects in their environment, allowing them to catch moths even in complete darkness. Similarly, dolphins emit a series of clicks and listen for the echoes, which helps them locate schools of fish. In the world of marine navigation, sonar technology uses ultrasound waves to determine the depth of water or locate underwater objects. Ships emit pulses of sound and measure the time it takes for the echo to return, calculating the distance to the object or the seafloor. These waves that we cannot hear have incredible applications, from medical imaging to navigation in the animal kingdom. Whether it's the ultrasound waves helping a mother-to-be see her unborn child, or the infrasound waves helping scientists detect nuclear explosions, these unseen and unheard waves play a vital role in our lives. Did you know that the medium through which sound travels can significantly affect its properties? Indeed, sound behaves differently in solids, liquids, and gases. Let's start our exploration with solids. When sound waves travel through solids, they move faster and farther because the particles in solids are closely packed together. This is why you might have noticed that you can hear someone knocking on the other end of a long table quite clearly. Now let's dive into liquids. The particles in a liquid are less tightly packed than in solids, but more so than in gases. Thus, sound waves travel slower in liquids than in solids, but faster than in gases. If you've ever tried speaking or listening underwater, you'd know that sounds are somewhat distorted, yet they can still travel long distances. Lastly, we have gases. Here, the particles are far apart, so sound travels slowest in gases. This is why sound takes a moment to reach you from a distance, say from a distant speaker at a concert. Now let's talk about something that's music to our ears, quite literally, the reflection of sound. When sound waves hit a hard surface, they bounce back instead of being absorbed. This rebounding of sound is what we call reflection. Ever shouted in a canyon and heard your voice bounce back? That's an echo, a perfect example of sound reflection. Sound waves hit the canyon walls and get reflected back to us, creating an echo. And what about the spectacular display of lights and sound in a thunderstorm? When lightning heats up the air, it expands rapidly and sends out a shock wave. This shock wave travels through the air as sound, and voila, we hear thunder. The world of sound is full of echoes and thunderous applause, all thanks to the fascinating physics of reflection and propagation. So the next time you listen to anything, remember the incredible journey that sound has made to reach your ears. Now, let's travel back in time to understand how our understanding of sound has evolved. In the early days of scientific exploration, sound was a mysterious force that intrigued thinkers and scholars. One such early experiment was conducted by Ernst Chladni in the late 18th century. Known as the father of acoustics, Chladni demonstrated how sound travels in waves by sprinkling sand on a metal plate and making it vibrate. The sand would then move to areas where the plate was not vibrating, creating beautiful patterns known as Chladni figures. In the 19th century, Lord Rayleigh, an English physicist, took these investigations further. He explored the physics of sound and wrote a comprehensive treatise, The Theory of Sound, which still serves as a fundamental reference for acoustic studies. These early experiments laid the groundwork for our current understanding of sound, and they've opened doors to various applications, one of the most significant being the reduction of sound reflections. Sound reflections, or echoes, can be a problem in certain environments, such as concert halls or recording studios, where clear, unobstructed sound is essential. Architects and designers have developed various techniques to reduce these reflections. One common method is the utilization of sound-absorbing materials like foam or carpet, which soak up the sound waves instead of reflecting them. Another approach is strategic design, where the shape and layout of a room are carefully planned to minimize echoes. For instance, in concert halls, the walls are often curved and covered with materials that either absorb or diffuse sound. This design helps to distribute sound evenly throughout the hall, ensuring that everyone, regardless of where they are seated, can enjoy the music without any distortions. The journey of understanding sound, from early experiments to modern applications, is a testament to human curiosity and innovation. So, what have we learned about sound today? We've journeyed together through the fascinating world of sound, delving into its very nature. We've learned that sound is a type of energy made by vibrations. When any object vibrates, it causes movement in the air particles. These particles bump into the particles close to them, causing them to vibrate too. This movement, called sound waves, keeps going until they run out of energy. We've also explored the intriguing realms of ultrasound and infrasound waves. Ultrasound waves, with their high frequency, are beyond the range of our hearing, but have invaluable uses. They help us see the unborn child in a mother's womb and guide submarines through the dark depths of the ocean. On the other hand, infrasound waves, with their low frequency, are also beyond our hearing range but can be detected by animals like elephants and used in weather forecasting. We've seen how sound behaves differently in various mediums. It travels fastest through solids because molecules are closely packed, a bit slower in liquids, and slowest in gases. We've also learned about the reflection of sound, which gives rise to phenomena like echoes and thunder. Our journey also took us back in time to the early experiments on sound. Pioneers in the field of acoustics laid the foundation of our understanding of sound, enabling the technological advancements we see today. We've learned how to reduce sound reflections too, to create better acoustics in a room, or to reduce noise in our surroundings. In essence, we've unraveled the invisible dance of particles that enable us to hear the world around us. It's quite a thought, isn't it? Every sound we hear, be it the melodious strains of music, the harsh clang of metal, the gentle rustle of leaves, or the distant rumble of thunder, all of it is but a symphony of vibrations. Sound, as we've seen, is a fascinating and complex phenomenon. Next time you listen to your favorite song or hear a thunderclap, remember the physics that make it all possible.